All right, in today's lesson here, we're going to be looking at our exponent laws here. So there's three main exponent laws that we're going to be looking at today, and they're illustrated here below. So our first exponent law that we're going to be working with here is the idea of multiplication. So when you have something like an exponential, let's take 2 to the power of 3, this as a whole is viewed as your exponential, and this here is referred to as your base, and this expression right here is referred to as your exponent. So here you have your base. This expression right here is your exponent, and the entire thing is called your exponential. So in this example here that we're looking at, this property that we're looking at, I should say, we have two exponentials that have the same base, and that base is x. And whenever you're multiplying, indicated by this dot symbol here, it could also be written like this. This also in mathematics means multiplication, just with the brackets next to them. Or sometimes they just put the expressions right next to each other. All of these mean multiplication. When you're multiplying with the same base, what you do is you add the exponents. You can see it's illustrated right here. I go ahead and add those exponents together. That's one of our rules. So like, as a quick example, just to illustrate this before we get into a bunch of examples of these, if I gave you something like 2 cubed times 2 to the 4th, I would be multiplying two exponentials, and those two exponentials have the same base. And because they have the same base and we're multiplying, we can add the exponents. This becomes 2 to the 3 plus 4, which is 2 to the power 7. And I've expressed this as a single exponential simplified, right? And there's nothing special about the number 2. It works for any real number at all. So we can have something like 2/3 to the power of 5 times 2/3 to the power of 7. And if you had that, you'd now be viewing this as my base, and this is my base, and I'm multiplying with the same base. Because of that symbol there, I'm going to go ahead and add the exponents, in which case this is 2/3 to the power of 12. Moving on to our next rule here, we have division. So again, when you're dividing, again, this relies on the same base. With the same base, what you're going to end up doing here is you subtract the exponents. And the order matters, so it's going to be in this case, a minus b. So the first expression divided by the second expression will be equal to that base, that is common. Going to need to have a common base again, to the a minus b. So as a quick example here, if instead of 2 to the 3 times 2 to the 4, I have 2 to the 3 divided by 2 to the 4, now I'm dividing with the same base, and that's going to end up being 2 to the a minus b, so 3 minus 4 is 2 to the negative 1 in this example here. And as a secondary example, it also works with fractions as well. You can have 3/4, and sometimes they even will write it non-linear, so there'll be 3/4 to the power of 3, and let's say 3/4 to the power of negative 1, let's say. And now I'm dividing with the same base. This is my base, this is my base, and you subtract the exponents. This time you have to watch out. This is going to end up being here 3 minus negative 4, and 3 minus negative 4 is going to give us 3/4 to the power of 4. So again, we'll come back to that in more detail later. And the last example here with this here is when you have power to a power. And by that, I mean, in this case here, you have an exponential, and here's the base, here's the exponent, and then you're taking that exponential and raising it to another power. So whenever you have power to a power, that would be this right here, you just multiply those powers together. So in this, as a quick example, if you have 2 cubed to the power of 4, that becomes 2 to the power of 3 times 4, which is 2 to the power of 12. All right, let's take a look at applying these rules to a bunch of examples and making sure we cover all the sort of finer points of these three properties. All right, so for our first example here, this is a direct application. You can see here I'm multiplying with the same base. I can just go ahead and add the exponents. This becomes 2 to the power of 8, as discussed. And likewise for this example here, multiplying with the same base, I can keep that base. So in this case here, that base is 1/3. You're going to add the exponents, becomes the power of 8. All right. The next one here, again, multiplying Bases are the same. They're both a 3. I'm going to add the exponents, and I was making the point here, it doesn't matter that the exponents are not just integers. You can deal with fractions as well. So in this case here, this is going to be following the rules, you can add the exponents together. So this becomes 3 to the 1/2. You can get yourself a common denominator, and this becomes 3 to the 3/2 for this example here. So same rules apply. Also, the rules apply if your base is a variable. So in this case here, my base is x, I'm multiplying. You just add the exponents. This becomes x to the power of 12. Continuing on here, you can also have a sequence of them. Don't just have to have 2. So in this case here, you can see base is the same, base is the same, base is the same. I'm multiplying, so we're applying this operation all the way across. So this ends up being y to the -3 plus 4 plus 6 is y to the power of 7. All right, let's continue. So you can also have various ones. It doesn't always have to be simplified together. So you'll notice here I can combine these two, and I can combine these two because these share like bases, and so do these ones here. So combining these two together, again, multiplication is a commutative operation, so I can interchange these two. I'm not going to explicitly write it out, but you can rewrite these so they're right next to each other. So then I am, in fact, multiplying with the same base, and this becomes 2 to the power of 12, and this becomes 3 to the power of 3. And again, I got that 3 because 4 plus -1 is 3. And that becomes my simplified expression for that one. Let's look at another. So same idea, but with letters now. So I can go ahead and combine these two together, and I can combine these two together. So this ends up being a to the power of 9 times c to the power of -3. And again, I got that just by adding my exponents together for both of these, including the minus signs, and you get the answer below. Now I'm moving on to our second property here with some examples here. We're going to divide, so I'm dividing with the same base. You subtract the exponents. So just to remind you, it's always the top minus the bottom. So 5 minus 3, and this becomes 2 to the power of 2. Continuing on here, again, I'm dividing, and my base is the same. So this will end up equaling 2/3 to the power of 3 minus 2 is 1. A lot of times in mathematics, if the exponent value is a 1, you don't write it down. So in this case here, just put 2/3, but either is fine. For the next example here, we're dividing. When you're dividing, you subtract the exponents. So in this case here, this is going to be 7 to the exponent of -3 minus -5. So that's my a minus my b, right? This is my a, this is my b. So doing this here, we end up getting 7 to the -3 plus 5, and that becomes 7 to the power of 2. All right, let's look at another. So this one here, again, sometimes they'll write it like this. If you prefer, you can rewrite it with the division symbol this way. At any rate, this becomes 2 to the -1. And for this question here, same idea. You're dividing. Also works for variables as well. So in this case here, we're dividing with the same base. Subtract the exponents becomes x to the 4 minus 7, which is x to the -3. All right, let's take a look at the next problem here. So for this next problem here, you've got a couple of operations mixed in. Before you apply Rule 2 for division, you can see I have a division symbol here, so I want to apply Rule 2. We really want to get this down to a simplified expression, so I make the observation I can put these two together. Through multiplication, this becomes x to the 8, y squared over x. Now the exponent on this x, if it's not written, is a 1, as we had discussed earlier, and the same thing with the y. So now I can kind of combine these two together through division, and combine these two together through division, and this ends up being x to the power of 7 and y to the power of 1, which again, sometimes people will just write a y. It doesn't matter. All right, let's take a look at the next one here. So for this one here, again, the same idea. Combine these two together because you can, and this becomes 2 to the power of 8 times 3 squared divided by 6. Now, a lot of times students will stop here and say, okay, well, I'm done. There's not more to do. But if you do make the observation that the 6 can be broken up, I can take this 6 and I can break it up into 3 times 2. Well, why would I want to do that? I'd want to do that because I have a 2 and a 3 in the numerator. So because of that, I now have 2 to the 8 divided by 2. And as we know, this is to the power of 1. And this is also to the power of 1. So this becomes 2 to the power of 7 times 3 to the power of 1, or just a 3. And then we can simplify our expression. All right, let's take a look at the next one here. Now we're in the situation of power to a power, and you guys know when you have power to a power, you multiply, so that becomes 2 to the power of 12. Again, same thing here, just to illustrate, it still works for fractions. The base here is a third, and this is power to a power, and it works for minus signs as well. So 2 times negative 6 is negative 12, and that's our answer for this one. Moving on to the next example here. Again, BEDMAS rules still apply, so you're going to go ahead and take care of the brackets first. And if I take care of the bracket, this becomes 2 to the power of 5, right? You're multiplying the same base, you're going to add the exponents. That's to the power of 3, and now power to a power, we multiply and we get 2 to the power of 15. And same thing here, this becomes 5 to the power of negative 21. And taking a look at this one here. So a lot going on here. Again, before you apply your division, you want to clean this up and get it to its most simplified expression, both in the top and bottom. So right away, I know I can change this to x to the power of 6 times x to the negative 5. The bottom I can write as x to the power of 4. And now I'm multiplying with the same base. I can add these exponents. This becomes x to the power of 1 over x to the power of 4. Now I'm dividing with the same base. I can subtract the exponents. It becomes x to the 1 minus 4, and that's x to the negative 3 here. That becomes our answer for this one. For this problem here, you'll notice the power of 3 has 3 bases here. This is a 1, and a 1. And typically when that happens, what this means, if you were to write it in the long way, it would be x, y, z times x, y, z times x, y, z. And you guys can see, because you can rearrange things, you know you can put your x's together, you know you can put your y's together, and you know you can put your z's together. So this ends up being x cubed times y cubed times z cubed, all divided by, I'm going to rearrange this so the x's, y's, and z's are just underneath each other, and we have this expression. So now you can see here, dividing these out here, this is going to give me x to the power of 1. And then taking care of this one here, we get y to the power of 2. And lastly, z to the power of 2. So this becomes x, y squared, z squared. All right, that concludes today's lesson. Just going through just some basics of exponentials with our 3 exponent rules here. Thank you.